Imagine standing on the surface of the earth, feeling the invisible pull that keeps your feet planted firmly on the ground. You drop a ball and it falls, you jump and you come back down. Gravity is so ordinary, so ever-present, that we rarely stop to question it. We take it for granted as if it's just another background feature of reality. But what if I told you that gravity is not only misunderstood by most people, but that even the greatest minds in history, Isaac Newton included, never truly understood what it is? And what if I told you that Richard Feynman, one of the most brilliant physicists of the 20th century, believed gravity remains the deepest, most mysterious force in the universe? Let's start with a confession. You don't really understand gravity. Neither do I. Neither did Newton. And that's not an insult. It's a fact that sits at the heart of physics. Newton gave us the first great mathematical description of gravity, a law so powerful that it could predict the motion of planets, the tides, and even the paths of comets. His law of universal gravitation is elegant and precise. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It's a formula that changed the world. But here's the catch. Newton himself admitted he didn't know what gravity actually is. He could describe how it works, but not why. In his own words, hypotheses non fingo, I frame no hypotheses. He refused to speculate about the mechanism behind gravity. He didn't know how the force was transmitted across empty space. He just knew that the math worked, and that was enough to launch the scientific revolution. This is the first great contrast in the story of gravity, the difference between description and understanding. We can describe gravity with astonishing accuracy. We can predict its effects, measure its strength, and use it to send rockets to the moon. But when it comes to the question of what gravity actually is, what causes it, how it operates at the deepest level, we are still in the dark. Richard Feynman loved to point out this gap between knowing how and knowing why. He once said, "I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong." For Feynman, gravity was the ultimate example of a force we can use but don't truly grasp. He admired Newton's honesty in admitting his ignorance, and he believed that real progress in science comes from embracing the mystery, not pretending it's solved. So what is gravity really? For centuries, people imagined it as a kind of invisible tether, a force that reached out across space and pulled objects together. Newton's law made this idea precise, but it didn't explain how the force was transmitted. Was there some kind of gravitational fluid filling space? Was it a property of matter itself? Newton didn't say, and neither could anyone else. Then, in the early 20th century, Albert Einstein changed the game. His theory of general relativity replaced Newton's force with a new idea. Gravity is not a force at all, but a curvature of space-time. Massive objects like the Earth and the Sun bend the fabric of space and time, and other objects move along the curves in this fabric. Imagine a bowling ball placed on a trampoline, creating a dip that marbles roll toward. This is the classic analogy for Einstein's gravity. But even this picture, as powerful as it is, raises new questions. What is space-time, really? How does mass bend it? Why does the geometry of the universe produce the effects we call gravity? Einstein's equations are beautiful and precise, but they don't answer these questions. They describe the how, but the why remains elusive. Feynman, ever the skeptic, was fascinated by the way gravity resists our attempts to explain it. He pointed out that unlike the other fundamental forces, electromagnetism, the strong and weak nuclear forces, gravity doesn't fit neatly into the framework of quantum mechanics. We have quantum theories for electricity and magnetism, for the forces that hold atoms together, but gravity stubbornly refuses to be quantized. The search for a quantum theory of gravity, a theory that would unite general relativity with quantum mechanics, is one of the greatest unsolved problems in physics. This is where the mystery deepens. Gravity is everywhere, shaping the motion of galaxies, the structure of the universe, the flow of time itself. Yet, at the smallest scales, in the realm of atoms and particles, gravity is almost unimaginably weak. A tiny magnet can lift a paperclip against the entire pull of the Earth. Why is gravity so much weaker than the other forces? Why does it dominate at large scales but fade into insignificance at the quantum level? No one knows. Feynman often used contrast framing to highlight these paradoxes. He would ask, why does gravity feel so strong in our daily lives, yet is so weak in the world of particles? Why can we describe its effects so precisely, yet have no idea what it really is? Why does the universe obey such simple mathematical rules, yet hide the true nature of its most familiar force? The more you learn about gravity, the stranger it becomes. Black holes, for example, are regions where gravity becomes so intense that not even light can escape. According to general relativity, the center of a black hole contains a singularity, a point of infinite density, where the laws of physics break down. What happens at a singularity? What is the true nature of space and time in such extreme conditions? These are questions that push the limits of human knowledge. And then there's the mystery of dark matter and dark energy. Observations of galaxies and the expansion of the universe suggest that most of the mass and energy in the cosmos is invisible, detectable only through its gravitational effects. What is this dark matter? What is dark energy? Are they new forms of gravity or something else entirely? Once again, gravity is at the center of the deepest mysteries in science. So the next time you feel the pull of gravity, remember, you are experiencing a force that has baffled the greatest minds in history. You are standing on the edge of a mystery that stretches from the smallest particles to the largest structures in the universe. And as Feynman would say, the real adventure is not in having all the answers, but in asking the questions that no one else dares to ask. In the end, gravity is a reminder that science is not just about answers, but about questions. It's about the willingness to admit what we don't know, to embrace uncertainty, and to keep searching for deeper truths. Newton didn't understand gravity. Neither did Feynman. Neither do we. But in that not knowing, in that endless curiosity, lies the true beauty of science and the deepest mystery of all.